and my gas sniffer are all calibrating outside. While this is calibrating, I'm going to do a basic interior or exterior walk around. While these are getting calibrated, I'm also looking for my gas meter. So right off the bat, I noticed that we have ventilated soffits. So when I do my attic inspection, I'm going to check and make sure that there's baffling that prevents the insulation from making contact with the edge of the soffit or the roof. I'm checking the exterior of the home and noticing the grade or the slope. Does it slope away from the home or in towards the home? And I'm also looking at the downspouts to determine if moisture is properly being diffused away from the home and that there isn't a grade or a slope back into the home in case there's a pooling or anything that could diffuse through the foundation and get back into the house. So I noticed our gas meter, and I'm gonna gas sniff it. My equipment is calibrated, showing 0.0. I have it set for LEL, or lower explosive limit, so that we can determine if the gas levels are correct. This is the utility side with the regulator. This is the residential side. If I did detect a gas leak on the utility side, it's their responsibility. If I detect a gas leak on the residential side, it's the responsibility of the homeowner to have that serviced. So with my gas detector going, I'm going to move slowly, no faster than 1 inch per second, along the joints and the fittings. If I get a positive reading, I'm going to apply a soapy solution to confirm that it's not a false positive. A soapy solution will bubble in the event that there is a gas leak. If I do get a positive with a soapy solution, I'll notify the homeowner they need to have the gas leak fixed. I also see flues. One is an intake and exhaust, most likely for our furnace. We'll get to that when we need to test that in a minute. But so far, the gas meter tested negative for any gas leaks. And again, we're looking for signs on the flashing or the siding of any kind of discoloration or any evidence of pooling or anything like that where moisture can get into the house. And I don't see any discoloration. That's a sign that there's good insulation in the walls. My equipment is all registering as calibrated. The first thing I do when I enter a home is make sure that it's a safe home for testing. So I'm immediately going to observe my carbon monoxide detector, and it's showing us that we are in a safe environment. While I'm here in the kitchen, I'm going to get my oven gas sniffing out of the way. This is an electric oven. However, if it were a gas oven, I would apply the same standards in terms of testing the gas line, moving no faster than 1 inch per second, and it's usually behind the oven if it's a standard conventional oven. Always open the oven doors and inspect that there are no items inside the oven when performing combustion testing on an oven. So at this being electric, I'm not going to worry about gas sniffing this. I'm going to hit another area for my gas detection. Typical ovens and kitchens have some sort of ventilation. If it exhausts to the outside, I would test that ventilation. However, this one does not exhaust to the exterior. So when I'm setting up the home in greatest depressurization, the fan is not going to have an impact on the pressure of the home. Just a basic inspection of the home. I'm looking for household chemicals that are often found inside a home. these can off-gas and impact the indoor air quality of the home. So we can make recommendations to the homeowner to remove these from this spot and find a safer place, preferably out in a garage or something that's not connected to the main home. I'm going to finish up with my gas detection down in the basement, where I'm assuming we have our combustion appliance zone. Here is our CAS, and I notice right off the bat that we have 2 gas appliances. So first thing I'm going to do is keep my carbon monoxide detector on my body and finish with the gas detection. The residential line that came in from the gas meter is right here, and it comes around. In a home, I would go along and test every single joint and fitting to ensure that there's no leaks, no faster than 1 inch per second, and apply the same standard. If there were detection from my equipment, to follow up with a soapy solution. If I got a positive reading from my soapy solution, notify the homeowner that they need to have the gas leak repaired. 10% is the LEL limit. So you can continue with an audit if you get an LEL reading less than 10%. Once you've achieved 10%, you can no longer continue with the audit. You have to stop. So looking at our water heater, for starters, it's a 2006 75 gallon, 76,000 BTU appliance, natural gas. We have our gas line, we have our emergency shutoff valve, our drip leg, temperature control. We have our sediment release valve. Up on the top, we have our cold water intake with the shutoff valve. We have our hot water that goes to the house. What's unique about this water heater is that it is an induced draft water heater. Most common are atmospherically vented, but this having the fan on top, you can see that it exhausts the flue gases immediately out of the house, so it's a much more efficient and a much safer unit. Moving over to our furnace, we also have a 2006 120 BTU furnace. We have the same drip leg, shutoff valve for the gas. This is called a high efficiency furnace because it has a sealed combustion intake and exhaust line. So both the air that this unit draws in and exhausts to are outside, which is the highest efficiency, and it's also the best for indoor air quality. What we have here is a supply to the home, and we have the main return system with an air filter. One recommendation I have is when replacing the air filter, to make sure that it's properly sized. The impact of having an open air filter slot like that is there's a lot of draft or air movement through here, and you can be pulling in things that could be off-gassing. So we have all these chemicals literally right next to the return. So every time this return turns on or the unit turns on, you could be, because of that open filter slot, pulling in the off-gassing and the chemicals that are all right here. You may not be able to detect it, but it's there, and long-term low-level exposures to these chemicals can be harmful to the homeowner. So my immediate recommendation is find a new place for these chemicals so that it's not right next to the return, and cover that filter slot. We have our emergency shutoff switch for the furnace. I would do an inspection of the interior as well, make sure there's no corroded wires, damage, cracked heat exchangers, anything like that. But other than that, that's pretty much the description of the furnace. So right now, we're going to begin our pressure testing of the home. And because we have an induced draft water heater and a sealed combustion furnace, the pressure and or the depressurization of the home is not going to make a difference on these appliances. However, I'm going to go through the motions so that you have an idea of how we would test these appliances in the event that you had an atmospherically drafted water heater rather than an induced draft. And an atmospheric, it just has the dilution, or the hood, the flow hood, it looks like a bell, with usually a metal pipe that just goes right to the exterior of the house. So that's how I'm going to perform the next steps as if we were working with an atmospherically drafted water heater and maybe even an atmospherically drafted hood on our furnace. For starters, we need to take our manometer with the hose in the red port. This is with reference to outside, which means I'm going to take my hose and run it to the exterior.
Is the house in any sort of condition or setup conditions right now?
We are currently in natural conditions, which means all interior doors are open and all exterior doors and windows are closed into the house.
Is the heating, air conditioning on?
The furnace is turned off. It's in the off position right now, and we'll be adjusting that as we do the testing. But natural conditions means that all fans, all furnaces, anything like that mechanical are off, and the other conditions that we talked about earlier with the doors and the windows. Thank you for bringing that up. So right now, in natural conditions, I'm going to get a baseline pressure for my CAZ, combustion appliance zone. So with reference to outside, this combustion appliance zone is pretty evenly pressured to the outside. It's moving around a bit, and it will continue to do so as it's a bit windy today. But you should see it normalize, and we're going to let that just hang out for a bit. What I'm going to go ahead and do is capture a baseline. This model of manometer does the calculations for you. If you're using a different model manometer that doesn't auto-calibrate or zero or baseline, then you have to remember to subtract your baseline reading from your greatest depressurization, which we're about to capture. I like to let it sit for about 30 seconds. I'm going to hit end capture. And now my manometer is pretty much zeroed out. It's going to fluctuate a little bit with the wind. But right now I'm showing a negative 1.7 baseline, which is really common and normal for a house like this. Just an inspection, brief inspection of the basement while I'm here. I'm going to come over and look at these joists. And I'm going to observe that they do have insulation in the joists, which is great. When I pull back the insulation, first thing I notice is all these spider webs. So when we have spider webs, that's an indication that there's a way for insects, spiders, and bugs to get in, which tells me, and which we just confirmed, that this joist is not air sealed. So we do not have a continuous and contiguous pressure and thermal boundary. We've got our thermal boundary, but as you can see, there's no air sealing, and I'm looking at the gaps between the wood, nails and things coming through, and that's why we have evidence of spider webs, because they set up shop near the air leaks, because that's how their dinner gets in. And they just crawl right in from outside, right into their webs. So spider webs are a great way to determine if there's air leakage in a joist like that. So great thermal protection, but we're lacking the pressure boundary, which is the air sealing, and that's a gap, it's not continuous. Okay, so what we've done now, our systems are off, our water heater is in pilot mode, we've got our baseline, and it's holding pretty well to the same number, it's roughly balanced. So I'm going to change the pressure in the house by turning on all of the fans, and my goal is to achieve the greatest depressurization for the home, formerly known as worst case scenario.
Does that include the dryer?
The dryer is one of the most important parts of that. So here's our dryer. I'm going to set it on air mode so that we're not running a dryer with the heat. Dryer is empty. So if that dryer is connected properly, it's going to take air from inside the house and move it out. This is a powder room. There's no fan here. We talked earlier about looking for the...
There is a fan. Do we want to use it?
No.
No?
No fans for the powder room.
Okay.
We talked earlier about the kitchen and the fan, the importance of the fan. It's a very powerful fan in the kitchen, typically 100 CFM. However, we don't have that in this case, so this kitchen is not going to impact the pressure in the home. There's a few steps involved in achieving the correct greatest depressurization. The first step is turning on all exhaust fans to full baths. Here's a full bath. Fan is on. I'm going to keep this door open. There's no bath in here and no return, so I'm going to close this door.
I think there is a return in this room. No? No. Never mind.
Is there a bathroom in here?
No.
Same for this room. No bathroom, no return. I'm going to close that door. And the same for here.
Isn't there has to be a return in one of these rooms though, doesn't there?
The return is typically a large grill. The main thing that we're looking for is the bathrooms with the fans.
One of these had a return. It's not mine. Alright.
Let's go ahead and move on and just remember that our main focus is the bathroom fans with a full bath and the proper door closures. This is an office. And it looks like we have a master bath. And a single fan. Closet there. And we'll keep these doors open. At this point, we may be at the greatest depressurization.
Do we close this half bath? Okay.
Let's go see what happened with our numbers.
What are we looking for?
Well, we're going to expect to see a negative number. And so from our baseline of negative 1.7 pascals, we increased the pressure, the negative pressure in the home by negative 2.2 pascals. Now, according to BPI standards, 5 pascals is the threshold. If we exceed 5 pascals, that means it's potentially possible for unwanted vented flue gas from our hot water heater or perhaps our furnace to be pulled back into the home. 5 pascals is enough pressure to make that happen. So as long as we're under 5 pascals, according to BPI standards, we're within the threshold and are okay to pass these appliances. But we're not done yet. So we have our negative 2.2 as a result of our dryer and our fans. We're going to see what happens now when we turn on our furnace. So I have my furnace system on heat. And I cranked it up. Most sealed combustion furnaces are 2-stage. They do 1 stage, which is just a fan, and you'll hear that, I already hear it, initial stage of the fan turn on. This is to blow out and control the ventilation of anything that might be in the ducts. And stage 2 just occurred, where the burners kick on, they start heating up the heat exchanger and the burner assembly, and then the air will flow through. As a result, the home has become 1 pascal more positive with the furnace on. So what I'm going to do is recognize that the furnace actually makes the home more positive. I'm going to go turn it off. If the furnace continue to make the home more negatively pressured, the last step, this is called the CAS door, would be to open and close that door. And see if it makes it go more negative. I like to double check. It's definite that the furnace makes the house more positive, so I'm going to turn that off. The system is off. Just like the 2-stage process for it to fire and turn on, it goes through the same 2-stage process to turn off. The burner assembly turns off, but the fan remains on to continue to give the homeowner the benefit of that heat and continue to exhaust the flue gases outside. We are at greatest depressurization, and we are at negative 2.2, where we were before we turned the furnace on. We can now begin testing our appliance. Again, we're going to assume that this is an atmospherically drafted appliance, as it is not right now. It's an induced draft, but we're going to pretend that it's an atmospheric. So first thing I'm going to do is I'm going to crank up the heat to the maximum setting, and I'm going to listen and observe very briefly. I want to make sure we're in a safe environment. So make sure that the burner turns on properly. And this one, you hear the induced draft fan kick on. It's going to do that 2-stage, similar to the other appliance. We have a very short amount of time to test the spillage on this appliance. You can take a phone or a mirror and 360 degrees, make sure that the spillage has stopped within 2 minutes. When a spillage occurs, under the draft hood, you'll see fog appear on the mirror or on the phone, indicating that instead of being properly exhausted out of the house, it is in fact drawing back into the house. Because remember, we're in greatest depressurization. We're at negative 2.2 pascals. One of the things that could cause spillage is that we don't have a proper rise to run. we're looking for a 1/4 inch rise to run in our flue. It's standard. It has to be at least 1/4 inch rise to run. Otherwise, we don't have rise with the heat. It can stay stagnant and it's more susceptible to be pulled back in. So I've done my 360 degrees. The appliance has not spilled and it's been 2 minutes. So this passes our spillage test. There's not enough negative pressure in this home, even in greatest depressurization, to pull flue gases back into the house, which is great. This is a 75,000 BTU unit. This is a 120,000 BTU unit. I'm going to begin combustion analysis of this. We always do the lower BTU unit first. My combustion analyzer is set up for natural gas. And here we have our oxygen. Our current weatherization shielding factor is 21. And it's ready for testing. The standard for BPI is to let this unit, this appliance, reach steady state before testing. So in order to do that, we don't want to just test it right away. For field exam purposes, we don't expect the proctor to wait, the standard time for steady state. So I'm going to begin testing. But understand, both appliances before testing, they have to be in a steady state. To complete the combustion analysis exam, you have to test one appliance of your choice. You can choose the water heater or the furnace. I'm going to give the verbiage on the water heater, and then we're actually going to turn on the furnace and test that, which we have to go back outside to where it exhausts. So right now, I've drilled a hole in our draft hood, and I've inserted the probe down into the left side of the turbulator, and I'm getting a reading of 7 parts per million. I take it out, I put it into the right side of the turbulator, and I get the same 7. So I'm calling 7 parts per million carbon monoxide exhaust from this appliance. BPI standard states that you cannot exceed the threshold of 200 parts per million for this water heater. So we are within the standards. This is a pass. I'm going to return this appliance back to pilot mode. This one's called vacation mode. They mean the same. I'm now going to turn back on our furnace and demonstrate the testing of the furnace with our combustion analyzer. And we're going to go outside. So because the furnace made the house more positively pressured, I had to turn it back off to get a good reading. It's convenient when the furnace makes the house more negative, because then it's still running while you're performing the testing, and then it's also achieving steady state. So right now it's in stage 1, it's starting to fire up again. Let's go out and see what kind of readings we get. But I just want to reiterate, before testing in a real home, you have to ensure the appliances reach steady state. That's typically 5 minutes. both the hot water heater and the furnace are both considered air-free testing. An oven, for example, is an example of an as-measured testing. The reason that the difference between air-free and as-measured is we're going to see our oxygen depletion go down from 20.9 and I'm guessing to around 5 or 8. Again, we have not achieved steady state, so we're not going to get the exact readings as if we were to allow this appliance to run for about 5 minutes or so. But as our O2 continues to drop, typically our parts per million of carbon monoxide will increase. This being a sealed combustion, 95% efficiency unit, 98 actually, according to our combustion analyzer, the result of that efficiency is 5 parts per million, which falls well within our threshold of 400 parts per million according to BPI standards. And we're right at about 9. That'll continue to drop. So this unit passes as it falls within the BPI standards. Our home is currently in the greatest depressurization. I'm going to return the home to natural conditions. At this point, if I had a combustion oven, I would test the oven similar to this to get our parts per million carbon monoxide for this appliance, which cannot exceed 225 parts per million. We're done with the combustion analyzer. I'm going to turn it off. I'm going to turn off the dryer. I'm going to turn off the heating system. And I'm going to run up and turn off the fans. And I'm going to reopen the doors.
Are you gonna open closet doors or no?
Sure. Their
Doesn't matter.
interior, it's going to have a minimal effect for testing, field testing purposes. Not a big for real life. I would open up all interior doors. Okay, so we're now ready to begin setting up blower door. The blower door is one of the most impactful tests because it identifies the size of the air leakage in a home by depressurizing it to negative 50 pascals with reference to outside. And it also tells the air changes per hour, which is important in determining issues if the homeowner complains of discomfort or high power bills. The blower door and some tools that come along with it can help us identify why that is. Part of the envelope is understanding the fenestration and where the leaks are, indoors and windows. The most cost-effective and equally effective way for a homeowner to reduce the gaps and the air leaks in their home is simply to inspect and maybe replace the caulking around the doors. Also, windows can be inspected because a lot of times there's a leak in the frame around the window, in the molding, which can be mistaken for a leak in the glass, which is what we inspect when we run our blower door. Caulking can fix that leak. But a crafty salesperson is going to have a homeowner replace their windows. If a homeowner is sitting, watching TV, reading whatever, and feeling a draft, that homeowner might mistakenly assume that her windows are leaky and seek to replace them, which is extremely expensive and has a very low return on investment, sometimes 30 to 50 years. A much more cost-effective approach is to inspect the windows and determine, with the blower door running, whether the leak is actually coming from the sill, from the sash, or most commonly from the frame, which can simply be fixed with some caulking rather than replacing the whole window. Other technologies exist. For example, there's acrylic window inserts that you can get with a urethane frame, so they're removable. You can put these inserts in instead of having to replace the window, and they act as a great sound barrier as well as an air leak barrier. We have a missing link on one of our crossbars, but no worry, we got it back up. Just as a good measure, give it a good tug and make sure that it can withstand the pressure when the blower door is turned on. This is our umbilical. It connects our manometer with reference to outside. We don't want the end of this hose, the reference, to be too close to the fan, so it's best to throw it out and to the side. I'm going to run down, grab the manometer.
Boom, 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 boom.
Now, when we take readings and use similar equipment, I still have a negative 1.7 Pascal baseline. So you can turn it off and back on, and that'll clear the baseline, or you can go in and clear it. It's really important. Your readings will not be accurate if you use a previous baseline. red to red, yellow to yellow. Red is our reference to outside, yellow is our reference to the fan speed. Once again, going to capture our baseline, let that run for about 30 seconds. Assuming it's been 30 seconds. Want to make sure that our ring configuration and our model match, because there's a dozen different configurations and model numbers. When you take the baseline, you want to make sure you have your cover on. And this is the correct configuration.
Ring A.
Correct.
Okay.
If you're unable to get a CFM reading, that just means the house is pretty tight and you need to add a ring. In which case, I would pop these out and then change the configuration. It happens. But as we are now, we should get a good reading. The house is in natural conditions. I closed the slider that we used to when we did the depressurization, and I had the hose outside. I closed that. So now with the home in natural conditions, we can set our pressure to 50 pascals. So we're going to see a little line with a circle. We want to make sure that we push that. What it does is calibrate to a much finer detail when the home reaches 50 pascals. If you can't quite get to 50, 28, 35, when you hit that button, it does the calibration as if the home were in 50, and it would give you the proper CFM. I just do it out of habit. CFM air leakage. What we do now is we do a walk around, preferably with the homeowner, and we identify air leaks in the house. And that's our fenestration, doors and windows, as well as recessed lights. We use equipment like thermal cameras, our feelers, and we can learn a lot about how air is leaking into the house and where from. Most of the time it's from the top plate, which is the attic. And we're going to do a brief attic inspection and determine some things that we see up there. But right now I can tell that the air is leaking in through the recessed lights and through all the penetrations in the top plate. To about 4,600. We can use those numbers and come up with some calculations to determine if we're going to have to add ventilation to the house. But for the time being, while that's running, let's do some envelope tests on the pressure and the thermal boundary. I need this manometer. So what I'm going to do is turn this off, and there's a manual configuration, this little knob here, that I can turn and get us back up to 50 pascals. You leave the two reference hose in, but you pull out the Ethernet. We are at 4,600. testing with the same appliance, you have to clear your baseline. So you can go in and hit clear baseline. And now I have 0 baseline. The manometer is going to return back to normal settings. You have to remember to clear that baseline, either turn it off or clear it manually. So now I'm going to take my pressure pan. I need a hose. So I'm going to grab the hose that we used here. It's a little long, but we'll make it work. Now, for our reference to the pressure pan testing, we want our reference to be inside the house with reference to the readings that we're getting on the pressure pan. So that means I'm going to insert our port into the blue port so that our reference is the wall space, what we're measuring, and the ducts. So with our blower door at 50 pascals, we can now do some analysis of the envelope. What we're looking for is somewhere under 2 pascals. 1 to 2 indicates there's not a whole lot of air changes moving through our walls. As we get into the 3, 4, 5, that means there's a considerable amount of air changes in the walls. And what that means is there's a direct connection to this wall to the outside. And the outside in this case is our attic. So we're up over 4 pascals there. Our duct system is another system that can be connected to outside. Very good. So we're with under a 1 pascal reading for our ducts, which is ideal. For the field testing, you test 2 places. So I tested one outlet down here. You can go up here and test another.
That'll break.
Very safely. So what this recessed light is indicating to us is that we are more connected we're still more connected to the inside of the house. And that's not good. We want a very strong pressure boundary between our attic and our conditioned living space. When we have that much air, and I can feel it, when we have that much air moving through these penetrations in the attic, it's a clear indication of where we need to focus our attention when in the retrofit stage, so that we can make cost-effective and effective solutions without wasting time in the wrong places. Right now I'm going to do a zone by zone. Making sure that this isn't pinched. We're looking for less, 1 or 2 is acceptable. As you get into the higher pascals, the higher the pascals, the less efficiency the more it tells us that this room is not getting adequate return. There's not enough return, and there's too much supply in this zone. And in closing the doors, just make sure we don't pinch the hose. When I close this, I can feel a significant amount of air blowing on my hand. So when walking around with the homeowner, this is a way that we can identify specific areas, and usually they'll tell us, this room is uncomfortable. It doesn't feel like it's getting enough air. And we have a very similar reading. There's just not enough return getting back to the system. It's oversupplied, and that positive pressure is inefficient and it's uncomfortable. We want a system that returns a 1-to-1 ratio. 1 Pascal of air, or CFM of air for every 1 CFM of supply. While we're here, we're all finished with the pressure and the thermal testing for our envelope. I'm going to turn off the blower door, and I'm going to get a fan reading. And to do that, I need my fan flow hood. Fan flow hood is set up in different stages depending on the size and the power of the fan. Most fans are inadequate and don't provide enough cubic feet per minute of air movement. We're going to determine if this is a good fan by the chart, the Pascal versus the CFM. According to BPI standards, 50 CFM is required for adequate ventilation. So I'm going to call it at 2 pascals. And we are in E2. So E2 with 2 pascals is 29 CFM, which falls short of the BPI standards and threshold for an effective fan. Another thing to note is this bathroom does not have a window. If a bathroom contains an operating functional window, it gets a 20 CFM credit. Had this bathroom had a window with our 29 CFM, it would basically pass. But since it doesn't have the window, it falls short of the threshold for being a good fan. The last step is we're going to do an attic insulation. We know, based off the readings with our manometer, that the house is fairly leaky, and that when we tested our recessed light and a couple penetrations in the attic, it was a lot of air moving through it. So at this point, I have a pretty good idea that I'm going to find some insulation here, but I'm not going to have any air sealing measures. Any kind of attic inspection, you want to have the right equipment, which includes proper respirator, which I don't have. Okay, so as I'm looking around the attic, I'm first noting the amount of insulation and the type. Currently, we have about 16 inches of loose blown fiberglass. which is a fair amount of insulation. That puts us right around 48, R48, as you get 3 R per inch. At about 16 inches of loose bone fiberglass, we're up and very near code. Where we're not, so that's the thermal, where we're lacking is in our pressure boundary. Although we have an adequate layer of insulation, we don't have any air sealing around the top plate. So all of these lights, all of the recessed lights, any electrical, plumbing, exhaust penetrations are unsealed, and at this point are connecting our attic or outside to our home. A couple things that I really liked about this attic is that it had baffling, which means it has the barrier from the insulation to the roof and the soffit, so that prevents contact with the insulation in the roof, which is really important for moisture and airflow. We had a ridge vent, we had soffit vents, so there's adequate ventilation for this attic, which is great. And I also saw sheathing around the exhaust flue. So there's adequate separation of insulation from any dangerous heating flues. The biggest recommendation I have for this home is to air seal. Move aside the current insulation, air seal with a spray foam, caulking on the larger holes, and spray foam, urethane spray foam on the smaller gaps, and that will create a tighter seal within the home, making it more comfortable and more efficient. That's it.
That's it.